Thank you very much, Kelvin, for the introduction. Thank you, Henry, for leading this whole CCAT effort. I'm really honored to give this presentation today about our ongoing project, CCAT project, CAV pilot deployment and development deployment in Midwest winter. And very honored to provide an overview of the research that we have been doing and partially supported by CCAT and also by our industry partners. And I assume most of you know this concept, so I won't dive into too much details about the background. Canadian automated vehicles, those are vehicles that can be driven by themselves, also cooperate with others. So it's not just autonomous vehicle by their sensors, but also connectivity between the vehicles and also vehicle and infrastructure, vehicles and the cloud. But the point I want to make here is we think those vehicles, although they are connected automated vehicle, we humans, either we are human drivers or human passengers, we are still the main subjects that those vehicles are serving for. So that's why there is still a huge need to think about humans while we're designing such kind of systems. Humans still are still in the loop. Humans are not out of the loop. So that's why we have been doing a lot of things about personalized autonomous driving, about human autonomy teaming. So which I will lay the background a little bit for today's presentation and then talk about the focus of our CCAT project, which is how we're going to address Canadian automated vehicles deployment in Midwest winter. But before that, as I said, human autonomy teaming is a very key fundamental element of connected automated vehicles, and our group has been doing a lot of work to model human autonomy teaming on CAVs, and we take this multi-model approach, as we call it. If you see from this figure, we break them down into 4 different layers. So the first layer is we directly model vehicle dynamics to model how humans they behave, they drive the vehicle. Things from the vehicle speedometer or their localization module. So we get to know vehicle longitudinal and lateral speed and acceleration, things like that, and we can make predictions about certain humans, their future lane change behavior or hard braking behavior, and those will be very important for us to inform the surrounding CVs about any anomalous behaviors. In-cabin monitoring is something that I started to look into after I joined Purdue in 2022. We also published a few papers about how we're going to model the driving behavior and also their anomaly using their gesture, using their head pose, or detecting their emotion by using an in-cabin monitoring camera, right? We have a camera that's looking inside of the vehicle, probably multiple cameras, and it can be considered as a smart cabin application. But the key thing is still here to model the human autonomy relationship. And the third is ongoing research that we are still trying to publish our first paper, where we use wearable devices, right? We use eye tracking sensor using those specified glasses, or heart rate monitoring, or ECG, EEG, or smartwatches like the one I'm wearing right now to check the underlying physical status of a certain driver/passenger and get to know their preference of a certain CAV while they are on them. The last one is really the topic, the focus of today's talk, and we think that's the most intuitive one, right? By directly speaking things out. As humans, we tend to express our feelings by saying words. So how are we going to leverage audio signal and specifically verbal command and to help out our autonomous systems to model and then better understand their preferences and then better serve those humans, either they are drivers or passengers. And that's where we have done the most recent research on. We published a lot of papers on those conferences and journals, and that's what I'm going to talk about today for the first part of the presentation. I'm going to cover CAV development with large language models, and then I will dive into the Midwest winter part during the second leg of today's presentation. As I said, audio signal, verbal command are the most intuitive approach for certain humans to express their feelings and allow our autonomous system on the CAVs to serve them, and then to model the surrounding environment and also to better behave in various conditions. But why do we need to use a certain approach compared to the others, right? So the conventional systems, as we're using nowadays, like our Siri or our Alexa, or those ones that are in your traditional vehicles that you're driving nowadays, we think they are struggling to interpret and adapt to the abstract instructions from humans. What I mean by this is a lot of times humans, they might have complex commands, or they have something that's not as intuitive as a system, I think. And they might be unable to interpret deeper feelings, emotions, or moods behind the verbal commands from a certain driver or passenger. And also for diverse speaking habits among individuals, they might also mean that same command can have different intentions by different people. And I always give this example out. These two people, either they are drivers or they're passengers, they are saying the same words, exact same words. The rush hour is approaching. But one people might mean you need to be as quick as possible to avoid traffic, while the other mean you need to be careful as the traffic will be complex. So it's the same sentence that they're saying to the autonomous system, which means actually opposite things by their preference, right? One is more aggressive, one is more conservative. So we think conventional systems on our vehicles or any systems, traditional systems based on natural language processing cannot really work very well for implicit commands. And that's why we look into large language models, right? I believe most of you have experience in using large language models like ChatGPT or Gemini or recently DeepSeek. But I want to stress this. We are using, yes, those large language models to help our CAVs to better reason, to better perceive, and also control. But we're not replacing any of the existing modules on our vehicles. So we still have the traditional modularized framework. We have perception, we have planning, we have control. But we are adding this layer to our existing module as an add-on feature. We're not replacing them. We're not doing any end-to-end as at least for now. But we are taking advantages of all the strengths by LMs, their interaction, their very rich expertise in understanding and reasoning, and just with zero or just a few shot planning. We use few shot planning in the research I'm going to present today, and also this continuous learning and personalization. So that can help our CAVs to better behave in this human autonomy teaming process. And as I said, it's an add-on feature. We're not replacing anything because of their hallucination might cause some safety hazards. And we also try to avoid real-time requirements. So I will show a demo to you so you know what I'm talking about. And again, this is just the background of our CCAT project. It's actually the second leg of this project was conducted during this project duration. So we were trying to lay the background for our project. And the way it works from a high level, here we show a flow chart here, is quite simple. It's quite straightforward. We try to integrate LMs into our autonomous driving technology on CAV to improve driving experience. And we switch on the system by saying things, a switch on command. Like here, it's just the word command. So you say command, it's like you say, hey, Alexa, to switch on a certain system. And the system will then be switched on, and then you provide your human command, whatever that is. And the command will also be combined with two other things. One is the context information. Another one is the system message. So the context information is, your route information, the weather information, or agenda that you might have afterwards and things like that. And the system message is your vehicle current speed, current acceleration, current position. So it's about the system that you're using. And then all those three things, they are combined and then sent to the large language model. And here, the model type doesn't really matter. You can use ChatGPT, you can use Gemini, you can use the Llama, DeepSeek, whatever. But we have done something to make the output of such LLMs into a program, we use the so-called CODAS policy. So the output of LLM will be codes that can be directly executed by our vehicle ECU. So if it's a planning command, then it's a code that can be directly connected to our planning algorithm on the vehicle. If it's control command, then it's a code that can be directly connected to the PID or MPC controllers of our vehicle. And that's it. That's the loop that we will have for a iteration. And then we also have this feedback loop, which is highlighted in green, where you can switch on the system one more time. You provide evaluation by saying evaluate. The system will be turned on. Start to listen to your feedback. You can say something like, that was good, or I want the vehicle to be driven faster, or things like that. And then also combine with the previous command, also the programs. Then they will be sent to the memory module as historic data. So for next time, after evaluation, for next time we switch on system by saying command, not just the new command that you say, but also the historical information, they will also be concatenated to your new command. So the whole package will be then sent to LLM to understand the historical interactions between yourself and the autonomous system, and then better serve this human autonomous tuning process. So that's pretty much about how it works from the high level. We use channel thought prompting. We use CODAS policy, so the output will be codes to be directly executed. And we also develop this memory module for personalized autonomous driving in various environment. So I will, I skipped some of the details for the first part because that's more like a background information for this project. But I do want to showcase the experiment video. Probably some of you have watched this video before. And we, split this window, which you will see in the video, into four different views. So we have this in-cabin view. You can see this passenger is not touching anything. So he's just a passenger, not a driver. You see this terminal, so that's the message that keeps communicating between the vehicle and the cloud. Specifically for this research, we use GPT-4. We use OpenAI's API on the cloud. So the information is actually sent to the cloud reason, and then sent back to our vehicle. This is an external view. It's more like a bird's eye view of our vehicle. And this is a real bird's eye view by the LiDAR map that we have at the top of the vehicle. So, we have three different scenarios for the first demo. The first scenario is about selecting the preferred parking spot for the human passenger who is going to watch a football game. The second scenario is an intersection scenario, an unprotected left turn intersection. The third scenario is a highway scenario where the vehicle is driving on a 3-lane highway and there is an aggressive vehicle driving in front of us. And for each of the scenario, there are actually two trips. One is before the memory module kicks in, and one is after the memory module kicks in. So you can see a difference on how LMs conducts this continual learning process and keep optimizing its performance based on the interactions between the human and the passenger and the vehicle. So with that, I will play this 5-minute video.
Command. The game is about to begin. I don't want to be late.
So you see the time it takes for each iteration. It's actually quite significant. It's not a very short time, real-time application.
Evaluate. Even though I'm in a hurry, next time you can park near the exit in order to avoid traffic when I leave.
This passenger realized, yes, I'm in a hurry right now. You park close, but it might take me forever to exit from the parking lot after the game is finished, right? Because there might be hundreds of vehicles.
Command. The game will begin in 5 minutes.
The second trip here, saying something still very implicit, high level, but based on the historical information interaction, this time the vehicle will find a parking space that's closest to the exit.
Evaluate. I'm satisfied with this trip.
You see, with these two interactions, the vehicle knows what the passenger means when he said that kind of high-level commands, and will find the parking space that's best suits the preference.
Command. I'm on my way to the emergency.
So the second scenario here is the passenger switch on assistant showing this urgency, and unprotected left turn, this vehicle decided to turn left before the other vehicle passed.
Evaluate. Even though sometimes I'm in a hurry, next time you should still wait for the opposite vehicle to pass.
So he thinks it's still too risky behavior, although he's quite late, but still try to make it feel more secure.
Command. I will be late for meetings.
Again, very similar high-level command. But this time, as you can see how GPT-4 reason is, it's in a hurry, but also concerned about safety. When you speed up, but also wait for the other vehicle to pass, and the vehicle starts to accelerate, wait there, using the LiDAR information to keep checking the surroundings.
Command. Let's continue turning when it's clear.
So you can keep feeding commands to the LM, to our system, and then this time, after checking the surroundings, that's the context information, the system message that I mentioned earlier, and then GPT-4 made the decision and turn left.
Evaluate. I'm satisfied with this trip.
And this passenger then provide another feedback to the system, and now GPT-4 knows about this whole preference. And the last one is a highway scenario.
Command. The front vehicle looks weird.
So we run into this kind of issues every day. You have crazy drivers driving a certain way, zigzag and whatever. And this time the passenger just describe it. GPT-4 made the decision to change it.
Evaluate. Next time, please directly overtake the front vehicle.
And this passenger was not happy about it. He didn't want to decelerate. He wanted to just overtake.
Command. The front vehicle looks very crazy.
And just by saying that simple command, the vehicle then decided to change it into a left, accelerate to the speed limit, and did a clear and smooth takeover.
Evaluate. I'm satisfied with this trip.
This overtake was appreciated by this passenger, and then here you go. It's another human autonomy process by using large language models. So here we talk about how we pave the road to where we are doing for this project. We are using that large language model to help our system to better serve for the humans and under different scenarios, and that's leading us to this project, which we're trying to see how that can also help us to behave, the CAVs to behave in different environments, right? So not just different scenarios, but also different environments. And especially here in Midwest, we have all kinds of weather types that might cause some troubles for our driving. So that's how we look into this. We think winter conditions can really create life-threatening risks that current autonomous systems might be struggling to address. And this is a picture that we took during one of our field trips on the test field. And you see the visibility is not as high as what I showed earlier, and also the lane markings are not visible at all. And in those kind of scenarios, how our CAVs are going to behave, right? The planning module, the control module, how are they going to be functioning? That's really what we want to address here. And just some facts out there, a lot of crashes are weather related, and our existing CAV, their sensor might face some degradation in different weathers. Of course, camera and LiDAR in low visibility environment that might have a major drawbacks. For radar, low visibility is not an issue, but when you have heavy storm weather, heavy snow, then the reflection might also downgrade your radio wave coming out of the radar. And land marking obscuration, for sure, you don't see any land markings when it's covered by snow, and also rapid surface condition changes and interference for GPS that can also happen. So how we're going to leverage our foundation models in this case to better develop and deploy our CAV systems here in Midwest winter. And we think all those things that we acknowledge and we're trying to address based on the framework that I showed earlier. So that was the basis that we built, and we want to make an extra step to address all those things, right? Perception failures, prediction uncertainty, planning challenges, and also this human autonomy mismatch, and how we're gonna require fundamental rethinking of those modules, right? Perception, planning, prediction, and human interaction. And that's how we think foundation models, large language models, and even more vision language models can help us to develop such a system. But before that, we also collected a lot of data by using our vehicle here, in Indiana during wintertime. We have all kinds of weather, snowy weather. That's the most common thing for extreme weather types, and night, during nighttime, and sunny, of course, but also we have foggy days, we have rainy days, a lot of rainy days during winter time. And we collected our own data and we fine-tuned the pre-trained model, foundation model using those data, so our vehicles can really be driven in a safe and efficient way in those kind of weather. So it covered a lot of things, and we are facing all those challenges, right? In snow intensities, ice conditions, and low visibility situations. So even for snowy weathers, right, they are different. Sometimes you have light snow, sometimes you have very heavy snow. I think we have a couple during this past winter. And the intensities can also play a role in your driving task. So how we're going to leverage vision language models to address all those and mitigate the risk of driving in such a weather environment. And also critical for safety system validation, we test model adaptability across diverse visual conditions, and we enable vision-based autonomy. So it's no longer just language-based system, but we also embed our vision part of it, we embed our perception part of it to make this happen. So how it works from the high level is we have the image input, we have a language input. The language input is very similar to what I showcased earlier in the previous demo, but we also have the image input here using our onboard camera sensor. So we keep taking images out there and we fit them into the vision language model that we pre-trained and we fine-tuned, and then directly generate control command, control policy. So compared with the previous demo that I showed, which was generating planning commands, here we are generating control command. So we're connecting the foundation models with different modules of our system, right? As I said, we're not replacing them, we're just connecting them with our existing module. Why we use vision language model, as some of you might have been working on this field and you know it probably better than I do. It has the visual perception information, and it can also combine natural language understanding from human and provide contextual reasoning for safety critical decisions, and also provide weather adaptive control parameters. We have done several winter specific control adaptations. We provide dynamic traction management based on visual cues. So the traction of our system will be tuned a little bit, not too much. We're not vehicle engineers, but we try to still make it a little bit customized based on the visual cues from the image. And the predictive braking can also be adjusted for variable surface conditions. So the way that your vehicles brake will also be based on the output of your vision language models. Speed profile adaptation, that's the key part that we did, especially when you have reduced visibility or when you have different scenarios. And route planning that considers winter-specific hazards as something that we are still trying to do, going to wrap up this project, and that will also consider a major part of the winter weather. So here's how it works in finer details. So you see, we have an input from both the verbal command and the camera images. The verbal command is from the passenger. The camera images are both actually in-cabin camera as well as in external camera, right? One facing inside at the passenger and one facing outside. We're taking those two as inputs together with the system message, as I said, describing the environment for the vision language model. We then fit them into our vision language model, and then the output of such a VLM will be the parameters for our controllers. So we have PID control for longitudinal speed control. We have MPC control for lateral lane control. And for each of those two controllers, we have 3 parameters that we can tune. Essentially, we're using VLM to tune those 6 parameters based on the inputs. And then you can generate such a system output, send those to our ECU of the vehicle, provide feedbacks, do the same thing as I said in the first part, and then you get the whole loop. So essentially, you are doing things with multiple inputs, with human commands, system message, stroke data, and camera images. And particularly, the work I'm showing today, we use the lightweight 8 billion parameter fine-tuned onboard VLM based on 201 model, Alibaba's model, for some reason processing VLMs, but the model itself doesn't really matter. We can use any existing model. DeepSeek, my students are looking to that, and probably Llama, but the architecture is what it matters for our research. And the output from VLMs are matrices, as I said, that can be directly used for MPC algorithms and PID algorithms for control. And we also use retrieval augmented generation for our memory module for personalized motion control. And by personalized, I mean not just the preference for different passengers in a certain traffic scenario, but also their preference in different winter weather conditions. And some other details, we use 4 NVIDIA A100 GPUs to train that, and every time it takes 5 hours to train the model, and we also use the training set from new scenes. And as I said, we also collected our own winter weather data, and we use those data for fine tuning. And we have 450 pieces of data for testing and fine tuning, and that covers diverse weather, diverse command directness. This is a demo that we did very similar to the previous one. There's like a overtake scenario. There is just a regular driving scenario, but the passenger have different feelings. We're leveraging those sensors. We have a LiDAR on our vehicle. We have 2 front cameras. We have a radar. So yeah, we collected a lot of data and we test that out in this controlled environment in Columbus, Indiana. It's a professional test track. It's actually a airport runway that's no longer in use, and we are using it. And I think the company Cummins is also using the other part of it. And we make those testing scenarios reproducible, which means it can be running there. It can be running probably MCD. It can be running in some other test field. Doesn't really matter because we have this whole system reproducible and portable, and it captures the full range of Midwest winter. So I'm gonna play a short clip of this demo video. We have another 5-minute video And also in this demo video, we did a lot of testing in different winter time, but during the heavy snow weather, which we did a lot of testing, it's not possible for us to fly drone. So we didn't actually capture any videos, but we have a lot of data that were collected and for our experiment. So the one that I'm showing is actually winter sunny weather, the perfect weather here in Indiana. But you will see how we personalize this whole thing based on both the vision and the language input to the system.
Come on, I feel a little bit motion sick.
So very quickly to pause here, you see actually two trajectories. One is more like a dashed lines, one is the solid red lines. The dashed lines is actually from the first trip where there's no VLM involved, and the passenger think this autonomous driving system is a little bit aggressive. He felt motion sick, so he want the system to be more conservative, but he didn't say that out loud. He just described what he felt, right? I feel motion sick. And this is longitudinal velocity. This is lateral velocity over time. So you will see that as time goes, the longitudinal velocity and lateral velocity, they are changing at a slower pace. So which means the acceleration both at longitudinal and lateral level, so this is PID algorithm, this is MPC algorithm, they are tuned in a more conservative, a milder manner, so that can make this passenger to feel better.
Good. Evaluate. Drive in a more gentle way.
But even that, this passenger still think it's aggressive. He still feel uncomfortable. So provide this feedback evaluation to the system, and let's see how the system will work for the third time.
Come on, I feel uncomfortable.
So the new line, as you can see here, compared to the previous one, as well as the previous one, it's even changing slower, right? So that's the slowest you can go, because we also set boundaries for both algorithms to be operated in, and this will make it a little bit more comfortable for this passenger.
Evaluate. It's a nice drive.
And you can just imagine, winter weather when it's pretty icy, you have all those black eyes after the snow, and you just describe, oh, I felt too scary driving like this, right? And then the VLM will take the input from the image. It will understand, okay, that's a icy situation, and then will further tune the parameters to be more conservative, right? To drive in a slower manner, and that can incorporate both vision as well as the language input and behave accordingly in a winter weather condition. So that's the whole concept of this. It's no longer just language, but we take image input, and based on the image input, based on vision input, we can then get all those different weather types and then make our CAV to be deployable in such a environment. And you can find more details in that demo video. You can find that online of our lab's YouTube account. But basically, we're not just doing demo for the sake of demo. We evaluate the system. We have a lot of metrics. We evaluate the system from safety, from efficiency, from comfort. We wanted to reach a high driving score. So it's not just guarantee safety, but sacrifice comfort, or guarantee comfort or sacrifice efficiency. No, we're trying to knock those things down at the same time. And as you see, compared to the baseline, our model, and we'll also compare with GPT-4o, actually, our model, our fine-tuned Q1 model can outperform those baselines in terms of safety, comfort, time efficiency, alignment to the needs from this human, as well as the overall driving score in most cases. So that showcase how our system can really behave in such a winter weather condition. And more importantly, the key metrics that we evaluate is a so-called takeover rate, right? A takeover rate is calculated by the frequency of you takeovers from autonomous system. If it's a level 1, level 2 system, as you're probably driving every day, you can have your hands on your steering wheel or slamming on the brake, and you take over from your ACC or LKA feature, right? For level 3, level 4, level 5, like the ones we're showing, we assume it's a level 4 system. A takeover can be the passenger press the e-stop button. There's an emergency stop button on the vehicle, or just deactivate by press the cancel button. We consider that as a takeover from this passenger on this autonomous system. And as you can see here, the takeover rate has been hugely reduced. And here, especially when you have baseline 44% without memory module, with VOM, but without memory module is 24%, and with VOM plus the memory module is 6%, which means probably before you drive for 100 minutes, you will take over 44 minutes. Or say you drive for 10 trips, you take over 4 trips. Now you only take less than 1 trip. So that actually build on the trust from this human passenger to such autonomous system in the winter weather here in Indiana. And some of the key findings, we showcase the personalization, the driving performance, the safety comfort that can be achieved, real-time analysis. That's a key thing, actually. Even for the ongoing one that I just showed, the best that we can achieve is still 1 to 2 seconds. So it's definitely not a millisecond level latency, which we are trying to address for our new CCAT project. We're trying to deploy everything on board, have an even more lightweighted model, so we can make things running at a faster pace, not every 1-2 seconds. We want it to be run like every 100 millisecond or 200 millisecond to make it really useful for safety critical situation. So that's something to be addressed. But our project has achieved many impacts: safety, mobility, equity, advancement, as well as the policy influence. We think we have nailed all those, and thanks for the team effort from my lab, and we're able to pretty much conclude this project with a very good result, and also some very nice publications on top conferences. With that, it's pretty much about this presentation. I want to acknowledge, of course, USDOT and CCAT for sponsoring our research, and we also have industry supporters from Toyota, from Bosch, and also AutoWare that has been helping us deploy such a system, and these are some of my wonderful students. And of course, this is not my student. Jeff Dean visited us last year, and we actually gave this demo to him, and he was pretty impressed, and provide some instructions for us to actually move forward. So I really appreciate it. And this student was not injured by VOM. He was injured by playing soccer, but because Jeff Dean is here, he really wanted to see Jeff in person, so he decided to still come and ask a few questions. But thank you everyone for attending this seminar, and I'm happy to take any questions, and thank you very much.
Thank you so much, Professor, for taking the time to do this presentation for everyone. All right, so we're going to open up the Q&A session. So if you do have questions, you can throw them in the Q&A box, or you can raise your hand and we'll unmute you. So we've gotten a few in the past couple of minutes. I'm going to address some of the ones that we received from folks who registered in advance. We received 2 questions that kind of touch on black ice that I'm hoping you can address. So I'll try and combine them into one. How well can the VLM and self-driving vehicles overall detect black ice?
We did some testing. It's not very ideal if we directly take off-the-shelf VLM without using our data, our collected data to fine-tune it. It's not the most ideal performance. A lot of times it's just ignored. But based on some information that we collected, the data that we have, it will keep improving, but still not at the level that we can say, deploy this tomorrow. So it often depends on more customized data that we collected. Say if we have more black ice data that's specifically from the vision from the camera, and then through a few examples, say this is a black ice and this is a near black ice, this is not a black ice, then definitely such a VLM will be increasing its performance. But so far, yes, it has some capability, but not very ideal.
Okay, great, thank you. Our next one. Thank you for your presentation. You mentioned that the LLM functions as an assistant to the existing control modules. In the video you showed where a verbal command indicated a passenger emergency, does that mean the vehicle would still proceed with the left turn without yielding to oncoming traffic, even if the LLM weren't involved?
Yes. So a little bit background of the whole system. For that demo specifically, even LM is involved, or perception planning control modules, they are also still running in parallel. So for that first scenario, when the vehicle turns left before the other vehicle to pass, actually our planning and control module, they are keep calculating time to collision. They actually make sure that collision won't happen, but it just happened to be that passenger feel it's too risky. So he provide that feedback to the system and say, next time, let's wait. But whenever that this passenger have a preference, the preference just a additional feature that can be considered for the plan and control module. What has the final say is always our existing planner and controller on the vehicle. So if, say, the passenger says something like, let's turn left before the other vehicle passes, let's drive more aggressively. But if the underlying safety barrier of the system is broken, if the control module, planning module think it's still too risky, then it will actually withdraw from that action and make sure that the safety is always guaranteed. So a short answer to your question, yes, to some extent, but the underlying rule-based safety check has been there to constantly check whether such a decision is safe or not.
Okay, they had a follow-up. Said, would using an LLM in this way potentially increase the vehicle's reaction and processing time? My assumption is yes.
Yes, that's definitely yes, and that's why we are proposing the new CCAT project, which we want to make things even more lightweighted. Because even for the second part of my talk, it's lightweight. It's 8 billion compared to the first one, which I don't know, 70 billion, 80 billion. But still, that takes 1-2 seconds and takes eat up some computational resources on our vehicle. So yes, it takes time, it takes computational resource, and we want to further optimize it.
Awesome, thank you. Our next one, can you talk a little bit more about the overall driving score that you mentioned towards the end of your presentation?
Yeah,
Your screen
yeah, thank you. So the driving score is more like a customized score. It pretty much just calculating, combining all those different metrics that we showcase. So we have safety metrics, time to collision, standard deviation. We have conform metrics like acceleration, jerk, and we have efficiency metrics, the latency, and also alignment metrics, how our output of VLM align well with the human's preference. So it's more like a weighted sum of all those different matrices and add them together, and we have the overall driving score. It's like if you're doing things about the new scenes data set. They have also a new scenes driving score. So it's more like a customized driving score.
Excellent. Thank you. Our next one. Hi, Professor Wang. Very interesting work. I am having a problem on the response speed for the VLM. According to my previous engineering experience, 10 Hertz is the lowest bound for vehicle controller's frequency, and you mentioned the response time is 1 to 2 seconds. Aren't the two conditions contradicting? How do you solve it during deployment and prototype?
Yeah, great question. And the way we do it is we only use VLM right now for high-level command. So, which means we're not using it for time-critical, safety-critical, time-step by time-step command, but we're using that for high-level command, like which route we're going to take, say, or what kind of preferred speed are you going to set. And those can be just one-time thing. You set it, you're good, and then probably 10 minutes later, you want to set another value. But for the things that you talk about, like 10 Hertz, every 0.1 second, you need to have an input. So far, at least what we concluded from our research, VLM or LM, they are not feasible to do that. We're trying to optimize it, but still, I don't think it's a power of LM. It's not the strength of LM. I think LM and VLM, their strength is to make that high level scene understanding or high level planning or control recommendation, and we still let our low level perception planning and control modules to handle all those safety critical, time critical decisions.
Excellent. Thank you. Hi, Dr. Ziran. I was wondering, have you looked into how the vehicle reacts in scenarios involving skidding due to snow or rainwater? Specifically, I'm interested in understanding the vehicle's behavior during such conditions.
Yeah, it's a great point, and thank you for raising that. It's beyond the scope of our research, at least for this research. And I think that requires probably a couple more mechanical engineers on my team. We actually have 2 mechanical engineering students put together this whole thing, but those low-level vehicle dynamics things, I think those are hard to model, and especially how you're going to connect VOM into that. And that's out of the scope, but I think it's going to be very important, especially here in Midwest in winter time. We might look into that in our next project.
Excellent. We have more of a comment from Daniel Bartz of VW. Daniel, if you're still here and you want to be unmuted, you can say your comment to Dr. Wang, or I can read it out, whatever your preference is. But while we're waiting, I'll move on to another question. What perception modalities, you've already talked about the vehicle sensors that you have on the vehicle, could you leverage infrastructure sensors to better improve your system, and what would that look like?
Yeah, that's definitely a yes. And that goes down to which stakeholder you're working with, right? Yeah, of course, if you're working with state DOTs or a federal government, then definitely want to leverage infrastructure sensor and make all those decisions. But as I said, this project is also partially sponsored by Toyota. As a car manufacturer, they don't want to rely on any external data, right? And even they don't want a cloud in there. They want everything to be on board. They want all the sensor inputs. They want all those inputs to their system are handled by themselves or the supplier that they work very closely, say Denso. So that's why, yes, if you have external sources of data like infrastructure sensor, you combine that with your own camera sensor, that will also tell a lot of things and fit them into vision language model. But it's a matter of who you are working with, what stakeholder and what they want.
Yeah, you have to come to Ann Arbor and use our connected environment to get that.
Yeah, look forward to that.
All right, Daniel, I'm going to allow you to unmute, so feel free to raise your comment. You should be on mute now, so you can ask your question.
Can you hear me?
Yep, we can hear you.
Okay. Yeah, it's a really interesting area. As a person who lives in Michigan, I'm a big fan of features that help me out with day-to-day driving when we get to some bad weather. I've actually done some research in this area and just had some thoughts that might be worth looking at for further research. Looking at the rawest data possible from the radar, the actual radar reflections was really helpful for things like radar slam. which we were able to use to figure out where our vehicle was, even when we couldn't see the lane markers and didn't have GPS. There's been some published research out there. I think Bosch has something where they've talked about better than 10 centimeters. But that really requires access to the raw data from the radar, but it might be something to look at. LiDARs that can produce multiple returns on each pulse, not just the first return or the last return, but integration of returns, is kind of useful, particularly when dealing with a lot of atmospheric obscurance. And then, one area I'm starting to look more into, I don't have a lot of firsthand experience with, unlike these other ones, but non-visible cameras, look very promising, particularly when you're talking about situations where you're in kind of limited visibility. So like detecting black ice, which I know came up, probably color cameras are not the right cameras for detecting black ice. Black ice is black at 1550 nanometers, and it's I think it's white at 905 or white or clear. So maybe looking at infrared cameras or other non-visible wavelength cameras, as opposed to just the visible cameras, it might be something to look at, and those are coming way down in price. So just some thoughts from having worked in some zero visibility type driving applications. So thanks again. Great research.
Yeah, thank you very much, Daniel. And those are very, very useful points. And actually, we are having some other project. We also work with another group at Toyota where we are using radar information to do a lot of stuff like you mentioned. Going back to the vision language model part or foundation model part, I think what is missing right now out there in the field is all this data are either language data, text information, or cameras data, right? Images, because those are the easiest to produce. We don't have that many data to train our models from LiDAR, and we don't have that many data for radar. So if you don't have that much data online available, publicly available, then there's no way for you to have a very good functioning foundation model to handle all that, and including infrared cameras, right? Because RGB cameras, they are the most dominant and they have the most data generated out of them. But when you don't have a lot of infrared camera images, and then it makes it hard for your foundation models to behave. But definitely, if you come up with some other methods using those sources, that can work out pretty well. But thank you for providing all those solutions. Those are amazing ones.
Great. We have time for one more question. So this is coming from another CCAT researcher who's doing some similar work to you. What perception mode is used to measure lateral position in the lane when lane lines are covered with snow?
Great point. And actually, we didn't ended up using anything besides the GPS, and because there's no way for us to do that when you have no it's covered by snow, then whatever LiDAR camera, it's not working, right? Because even for humans, we cannot see that. So that's why we leverage our GPS to at least locate the vehicle at a certain lane if we have a preview map. And that's the most challenging part, right? And a lot of times, if we're using VLM for scene understanding, scene reasoning, it will just provide you with a feedback, say, hey, this is not drivable. Now the situation probably is not a good time for driving. Probably you should just take a rest. And that's also the power of VLM. You can just provide that scene understanding to you instead of making very risky decision or recommendation.